Welcome student to the class of antenna and wave propagation. Today we will discuss about the line surface and volume integral. So starting with the line integral. The line integral can be written as suppose we have a given vector A, and this vector is passing through an arbitrary line of length from A to B. This vector is passing through a length of arbitrary length, that is the length of A and B. Now to evaluate the line integral on this arbitrary length, we consider a small incremental length dl. Then the total line integral of this vector on this line can be written as L A dot dl. That is, which can be written as from length from point A to B, vector A dot dl. So the line integral A dot dl is the integral of the tangential component of A along curve L, and this is the tangential component of A along the curve L. So A dot dl is the tangential component. So we also the equation can also be rewritten as dot A dot dl. So magnitude of A into cos theta dl. Magnitude of A into cos theta dl. Now suppose if we connect this point, the point A from point B. Now the line is closed. So this integral changes from closed line integral of vector A along the length dl. So this line integral changes from open path to closed path along for vector A along the length dl. This closed integral is also called circulation of A. Circulation of A. This closed line integral along the length L for a vector A is called circulation of A around L. Circulation of A around L. Here the diagram is shown here. We have considered a small incremental length dl, and the angle subtended by vector A to the line L is considered as theta. This is the path of length L from point A to B. Now if we close this path, that is we consider travel this path from A to C, C to B, then it is called closed line integral. It is called closed line integral. So this is a line integral on a given for a given path of a vector A. Now surface integral. Surface integral. Consider a surface. Here consider a surface which is bounded by a closed line. Consider a surface which is bounded by a closed line. Now there is a vector field A which is passes through this surface. There is a vector field A, consider, which passes through this surface. Now take an incremental surface ds on this and draw a perpendicular vector from this surface, say an, normal vector. So the surface integral phi can be written as magnitude of A cos theta ds, or A dot the normal vector. We have considered the normal vector A dot dl into ds. In the previous equation, we have directly used A dot dl, that is the tangential component along the length. But here we have used the tangential component along the normal vector from the surface. See, if we consider a Cartesian coordinate system, say, and we have a normal vector in the direction of ax. So we have variable dy and dy and dz. So here the differential surface for this figure can be written as dy into dz along the normal vector ax. Therefore, in the surface integral, a normal vector is used and the differential surface along that normal vector is considered for here in the surface integral. And the differential surface integral in all the three coordinate systems we have already discussed. How we take the surface along the normal vector in the Cartesian, cylindrical and spherical coordinate systems. So this is the surface integral. In the Gauss law, we consider phi E as an electric flux which is equal to the d dot ds, that is the surface integral of the electric flux density, and this is total electric flux. Here also, if we consider this surface as a closed, if we consider the surface for closed surface, that is the surface defining the volume. That is the surface defining the volume. Defining the volume. This line integral, open line integral can be rewritten as phi is equal to closed surface integral of d dot ds. D dot ds. So when for a given closed surface, if a flux is coming out, so this is called a net outward flux. Net outward flux. This is just like that. If suppose you have a motorcycle, tire of motorcycle or car, anything. Now I have a small hole in this tire. This tire is completely filled with air. Now from this small length, the air will be come out from the tire. So this air that is coming out on the given surface is called flux here, and this is the normal to the surface. This flux is coming out normal to the surface, and this small area is the ds. So in the similar manner, when charge q is placed on a surface, this charge, so due to this charge, a net output electric flux is coming out from the surface. If the effective charge is positive, then the direction is outward, and the effective charge is negative, then the direction is inward. So for a given vector, A dot ds is called net outward flux, and in the previous line integral for a closed integral. Both cases are for closed. So we summarize for surface and line integral. We summarize it for line and surface integral. The closed line integral of A dot dl is called circulation. However, the closed surface integral of vector A along its normal vector to the surface ds is called net outward flux. So here in this equation, this denotes the net outward flux. The net outward flux of A from S. Now we will study next in the next classes how the surface integral can be converted into the volume integral and how line integral can be converted into the surface integral. So again we have studied the line integral, we have studied the surface integral, and we have seen the case of closed line integral and closed surface integral. The closed line integral is called circulation of a vector A, while the closed surface integral is called the net outward flux of vector A along the surface S. Now the volume integral. The volume integral can be simply defined as volume integral the volume integral simply can be given by the volume integral of A dV. We all are familiar about the Gauss law, and in the Gauss law, the total charge in the Gauss law that is the total charge on a given volume is equal to the volume integral of the rho v dv. Here rho v is volume charge density and its unit is coulomb per meter cube. So this is in meter cube. So meter cube, then this meter cube is cancelled out and we get coulomb. So the dimension is verified here. So this is the line integral, surface integral and volume integral. Now have a look on the numerical. Here we have a given vector f and we have to evaluate its circulation along the given path. So what is the path? Here is the figure. The path is divided into the four sections, section 1, 2 and 3 and 4. The section 1 is directed in the x plane from point 1 to 0. Section 2 is directed in the y plane from point 0 to 1, while section 3 is directed from uh, it is directed from it is in between xy plane, xz plane. So at y equal to 1, it's vary from y equal to 1, it's vary to z equal to 1 and x equal to 1. Similarly, the fourth line is from downward direction to the x-axis, that is from z equal to 1 and y equal to 1 to x equal to 1 and z equal to 0 and y equal to 0. So to evaluate the line integral here, we have to, this is a closed path. This is the case of the closed path. So to evaluate the line integral here, we have to divide uh, these paths into four subpaths. That is path 1, path 2, and path 3 and path 4. Because these path has the direction of the vector, the unit vector, that is the direction of all these paths are different in different situations. So the closed line integral f dot dl we have divided into four different parts. So these paths we have seen in our figure. Now taking path 1. The path 1, in path 1, the x varies from, in path 1, the x varies from 1 to 0, and here z equal to 0, 1 to 0, and here z equal to 0 and y equal to 0. Z equal to 0 and y equal to 0. Here z is 0 and y is also 0. So we have these three components along the path 1. So putting these values in the vector f, where the path is broken now for segment 1 y equal to 0 and z equal to 0. So this term is 0 and this term is 0, and the direction of the line is in the x direction. So dl can be written as dx ax as we have discussed in the differential length. Now the value of the line integral in path for path 1 can be written as, we have only this ax direction, so x square dx ax, x square dx, and x varies from 1 to 0, 1 to 0. Um, Integrating this x square, we have minus 1 by 3 along path 1. Now for segment 2, this is segment 2. The segment 2, the y varies from 0 to 1. The y varies from 0 to 1, and here in segment 2, z equal to 0 and x equal to 0. So x and z components are 0, only the y components is varying. However, we can see that this is 0 and this is 0. But the ay component, that is when y is varying in the direction, it does not contain any terms of y, and also x and z are 0. Therefore, f dot dl is equal to 0 in for segment 2. For segment 2, f dot dl is equal to 0. Okay. Now consider our path for segment 3. Segment 3. For segment 3, this is the segment. The y is 1 throughout. That is, the y is not 0. The value of y is 1 throughout, and this line shows a linear linear path that is a linear relationship with z and x. So y equal to 1 and x is very linearly with z, or we can say z is very linearly with x, that is as when x equal to 1 z equal to 1, x equal to 0 z equal to 0, x equal to 3 z equal to 3, x equal to 4 z equal to 4, and so on. So here we can write x equal to z also. So we have two varying paths. One path is along ax direction and one path is along az direction. Therefore, the equation, uh, we have two terms, that is one along ax direction and one along az direction. However, these the length for y is constant and is not varying. Therefore, ay component is not present here. So the differential length along the path segment 3, along the path of segment 3 will be dx and dz. Now f dot dl is equal to x square dx minus dz. Dot product of these two components of vector f with the differential length along the x and z direction. We only get x square dx minus dz. Here we have seen that z equal to x, therefore dx equal to dz. So we converted this line integral, that is we rewritten this dz as a dx. So dz equal to dx, therefore the whole equation, integration equation become x square minus 1 into dx. So x square is x cubed by 3 minus x, putting the limit from 0 to 1. Here we see that the x and z are varying from 0 to 1. Therefore, we have put the limit of x or y, that is 0 to 1. We get minus 2 by 3. Now for path 4. For path 4, the x is 1 throughout. The, the x is 1 throughout. The y and z components are varying. The y and z components are varying and it has a linear relationship with each other. That is, the y and z are varying from 1 to 0. Since it is a cube of unity cube, therefore 1 to 0. In the previous section, we have discussed it in general sense, but here in this case, for path 3, it is a unity cube, therefore it will vary from 0, 0 to 1, 1. So for path 4, same situation is applicable, but it is varying from, the slope is negative here. That is, it is varying from higher value to lower value. Therefore, in path 4, we have z equal to y and x equal to 1 throughout. So the integrals, the vector f, we have only varying component of y and z. Therefore, we write minus z dz plus y square, minus z dy plus, minus z dy and minus y square dz. That is this. Now we have z equal to y. That is the linear relationship, that is z equal to y. Therefore dz equal to dy. So putting dy instead of dz, we have minus y square dy, and the limit is varying from 1 to 0. So putting the limit and integrating, we get 5 by 6. Now the total integral f dot dl will be the sum of all the segments, that is from path 1, path 2, path 3 and path 4. So path 1 we get minus 1 by 3, from path 2 we get 0, from path 3 we get minus 2 by 3, and from path 4 we get 5 by 6. Adding all this value, we get minus 1 by 3, 0, minus 2 by 3 plus 5 by 6, that is sum up to minus 1 by 6. So the final answer for this line integral is minus 1 by 6. So here in this class we have discussed the line integral, the surface integral and the volume integral. And in the previous class we have discussed the differential length, the differential surface and the differential volume in all the three coordinate systems. So these three integrals, the line, surface and the volume, can be, and the differential length and differential surface and differential volume can be used in these integrals in to compute the line, surface and volume integrals in all the three coordinate systems, that is the Cartesian, cylindrical and spherical. So the numerical will be according to that in the different coordinate systems. Here we have discussed the case of the Cartesian coordinate system. In the similar manner, we can able to evaluate the line integral in cylindrical by using the differential line length by using the differential length in cylindrical coordinate. In the similar manner, we can evaluate the surface integral in cylindrical coordinate system by using the differential length we have discussed in the cylindrical coordinate system. And similarly, the volume integral can be evaluated by considering the uh, differential volume defined in cylindrical coordinate system. The same situation is applicable to the surface integral, that is, we have considered the differential length, differential surface and differential volume in the spherical coordinate system, and using that differential length in evaluating line integral, using that differential surface in evaluating line surface integral in spherical coordinate system, and similar in the similar manner using that differential volume while in the if I, in the evaluating of the volume integral in spherical coordinate system. So in the uh, so in the next class we will discuss about the del operators, how the del operators are used uh, for converting. Del operators are useful in the three-dimensional space, three dimension, and we will try to make this del operator and numerical based on that. These del operator, that is generally these del operators are used in generally three ways, that is the gradient, divergence and curl. So these three del operators are used in all the three coordinate systems, that is the Cartesian, cylindrical and spherical. And we perform some numerical calculation using that del operators. Uh, these del operator has some mathematical applications also. That is, we have discussed in this class to convert the line integral into the surface integral, which is called divergence. Sorry, to convert line integral into the surface integral, which is called Stokes theorem, by using Stokes theorem, and surface integral to the volume integral by using divergence theorem. So these three del operator, the del operator is very useful for the vector calculus. So that's all for today. Thank you.